Hello everyone! Have you ever thought about becoming resistant to cold? Doing activities in freezing weather, taking a cold shower without convulsing, or even living with little or no heating in winter? Well, I have a theory-based way to help you tolerate the cold more easily using nutrition. Not to make you 100% immune, but to make things more comfortable. Before I go any further, I want to be crystal clear. What I'm going to talk about is mostly theoretical. There is no direct scientific proof yet that this exact diet protocol will make you more cold resistant. But what you're going to see in this video is largely fact-based, and I leave the sources in the description. And of course, this does not mean you should go out and freeze on purpose. Always be safe with cold exposure. Alright, back to the subject. This video is split into 10 segments: anatomy, histology, cellular biology, biochemistry, chemistry, zoology, food chemistry, nutrition, physiological anthropology, and a conclusion. Try not to skip parts, so everything will make sense as a whole. So, what keeps us humans from getting cold without clothes or any external heating, just using what your body has? If you thought of that, then good job, that's right. The fat on our body is like our natural clothing. It insulates us, so that the heat from inside doesn't escape so easily, just like the walls of a house that keep the cold outside and the warmth inside. Now you might think, oh, so being fatter keeps you warmer? In short, yes, more body fat generally gives more insulation. But that doesn't automatically mean you're healthy. And I'll add another but. You can be at a normal, healthy weight and still be quite resistant to cold. How is that possible? Besides the amount of fat, other things matter too. How your blood vessels react to cold, your muscle mass, your brown fat, brown adipose tissue, and what I'm focusing on in this video, the composition of your body fat. The scientific term for body fat is adipose tissue. This adipose tissue lies under your skin, and depending on your body fat percentage, body region, and gender, it can be thicker or thinner. It can also be found inside the body, for example, in the mesentery. There are also places where too much fat is not good at all, like in and around certain organs, or as cholesterol-rich plaques in your arteries, which can lead to atherosclerosis. The hypodermis, or subcutaneous tissue, is mostly adipose tissue, and is the deepest layer of our skin. This is the layer that protects us the most from the cold. Adipose tissue is made of many elements, but the stars of the show are the adipocytes, also known as white adipose cells. These adipocytes are the real fat reservoirs of our body. Now we're getting deeper into science, but don't worry, I'll keep it understandable, even if you're not into biology. An adipocyte kind of looks like an egg yolk, doesn't it? Or is it just me? Some of you might know what a classic cell has: a membrane, cytoplasm, nucleus, mitochondria, the famous powerhouse of the cell, Golgi apparatus, and other organelles. Adipocytes have all that, but they also have a special feature: a lipid droplet. You can think of it as a big internal fat reservoir. This giant droplet fills almost the entire cell and is where most of the stored fat is located. So, what's inside this fat reservoir? Inside the lipid droplet, we mainly find triacylglycerols, TAGs, about 90 to 95% of the stored fat, cholesterol esters, fat-soluble vitamins like A, D, E, and K, small amounts of diacylglycerols, and monoacylglycerols. We're going to focus on triacylglycerol. This molecule has two main parts: a glycerol backbone and 3 fatty acid chains attached to it. If we look at all the fatty acids stored in human adipose tissue, on average, they tend to be roughly saturated fatty acids, SFA 20 to 30%, monounsaturated fatty acids, MUFA approximately 50 to 60%, polyunsaturated fatty acids, PUFA approximately 10 to 20%. These percentages depend a lot on your diet, but this is the general ballpark. Now we go even deeper. From here on, a bit of science background helps, but I'll still keep it as simple as possible. Each fatty acid has a melting or freezing point, just like any other organic compound. For common long-chain fatty acids, the approximate melting point ranges are SFA approximately 40 to 73 degrees Celsius, MUFA approximately 0 to 28 degrees Celsius, PUFA approximately -55 to -5 degrees Celsius. These numbers are for pure fatty acids in the lab, but they still show us a pattern. The more double bonds a fatty acid has, the lower its melting or freezing point. Now we focus on polyunsaturated fatty acids. Some famous PUFAs are LA, DHA, TPA, EPA, linoleic acid, and arachidonic acid. Among common PUFAs, one of the highest freezing points, linoleic acid, starting to freeze at around -5 degrees Celsius, a bit lower than water. One of the lowest, EPA, with a freezing point around -55 to -53 degrees Celsius. Also very low, DPA, approximately -54 degrees Celsius, and arachidonic acid, -51 to -49 degrees Celsius. DHA, about -45 to -43 degrees Celsius. ALA, about -13 to -11 degrees Celsius. So PUFAs stay liquid at much lower temperatures compared to saturated fats. This might not look like human medicine at first, but it's important to make the whole picture make sense. Name me 5 Arctic animals. A lot of you probably thought of polar bears and penguins. Maybe also walruses, seals, and beluga whales. And what else lives in cold northern waters? Fish. What kind of fish from these waters can you find in the supermarket? Salmon, cod, herring. These can live in very cold waters. Seals live in the Arctic as well, and can swim in cold waters for long periods. These animals survive extreme cold thanks, among other things, to their body fat and cell membranes. Their blubber and fat stores are rich in mono and polyunsaturated fats, especially MUFAs, and in many marine species, long-chain omega-3 PUFAs. This helps their fat stay more flexible and less waxy at low temperatures, and keeps their membrane fluid in the cold. Their thick hypodermis, made of adipocytes full of unsaturated fats, doesn't turn stiff as fast as mostly saturated fat, and helps their tissues and cell membranes stay functional at very low temperatures. When it's too cold, the mitochondria in brown fat, brown adipose tissue, BAT, start burning fat to make heat. They oxidize long-chain fatty acids during this process. Many of those, especially in cold-adapted and hibernating animals, are MUFAs and PUFAs, and long-chain fatty acids are the ones that activate UCP1, the main heat-producing protein in brown fat. Bears use all of these during hibernation. They go into winter with fat stores enriched in unsaturated fats, and their brown fat is crucial when they need to produce heat again. To make this more concrete, scientists have actually measured how unsaturated the fat is in some cold-adapted animals. In gray seals, about 79% of the fatty acids in blubber are unsaturated. In several seal and dolphin species, blubber oils have around 62 to 78% unsaturated fatty acids. In the Ganges River dolphin, blubber oil has about 72 to 73% unsaturated fatty acids. In Antarctic seals, like crab-eater seals, MUFAs alone can be close to 60%, plus 20 to 25% PUFAs, reaching total unsaturation of 80 to 85%. So in these animals, the majority of their blubber is unsaturated fat, perfect real-life examples of the more double bonds equals more fluid fat rule. How cold can they actually go? Weddell seals swim and dive in seawater around -2 degrees Celsius, under sea ice that stays frozen most of the year, in air temperatures that can drop below -50 degrees Celsius. Polar bears keep a core temperature around 37 degrees Celsius, while roaming in -40 to -50 degrees Celsius air. They do this with thick fat, plus highly insulating fur. Their fat comes mainly from the seal blubber, which is rich in unsaturated fats. Cold water fish, like salmon and Arctic char, live and grow in waters just above freezing, and can survive as it approaches about -0.5 degrees Celsius. Their membranes are loaded with PUFAs, especially omega-3s, which keep them from turning rigid in near freezing water. All of these examples show the same thing. It's not just how much fat you have, it's also what kind of fat. A thick layer of fat that's 70 to 80% unsaturated is much more flexible and effective at low temperatures than the same thickness of mostly saturated, harder fat. This quality over quantity idea is exactly what I'll apply later when I talk about the Inuit, and how changing human body fat composition towards more unsaturated fats could, in theory, improve our cold tolerance. Now let's talk about food, especially food rich in polyunsaturated fatty acids. On the regular market, there isn't a huge variety of true Arctic foods. They can be expensive and hard to find, so I'll give you a top 10 of foods highest in total PUFA and a top 5 of foods highest in EPA. Exact numbers vary between sources and brands, but these are good approximations. Top 10 foods with the most PUFA per 100 grams, mostly cold pressed oils. Safflower oil, 74.6 grams. Grapeseed oil, 69.9 grams. Flaxseed oil, 67.8 grams. Sunflower oil, 65.7 grams. Walnut oil, 63.3 grams. Poppy seed oil, 62.4 grams. Wheat germ oil, 61.7 grams. Soybean oil, 57.6 grams. Tomato seed oil, 53.1 grams. Corn oil, 52.9 grams. Top 5 foods with the most EPA per 100 grams, mostly marine oils. Manhattan oil, 13.2 grams. Salmon oil, 13 grams. Sardine oil, 10.1 grams. Bearded seal oil, 9.7 grams. Cod liver oil, 6.9 grams. Some of these, like cod liver oil, are closer to supplements than normal foods. Obviously, don't check the bottle. Vitamin A overdose is no joke. Always use this within safe doses. Until now I've presented mostly accepted facts, but here comes the big question. Does eating food high in PUFA and EPA actually make a person more resistant to cold? Most scientists would say, we don't have direct proof in humans yet. There are no large clinical trials where one group eats an Arctic-style diet and then gets tested in a freezer. But I think there's some truth to this idea, and I want to show you why my point of view is at least plausible. First of all, if a person reduces saturated fat intake for a long enough time, the SFA, MUFA, PUFA proportions in their fat stores will gradually change. Adipose fatty acid composition reflects what you eat. Over time, you get less SFA and more MUFA or PUFA in your adipose tissue. However, saturated fats can still form inside the body through de novo lipogenesis, DNL, where excess glucose converts to acetyl coenzyme A, resulting palmitic acid, a saturated fat. Palmitic acid can be elongated to stearic acid, and then, via the enzyme ACD1, converted into oleic acid, MUFA. So what if we also limit carb intake so we don't have too much excess glucose for DNL? Well, then we end up with a ketogenic diet, or at least a very low carb, high fat diet. On top of that, there are studies, mostly in animals, showing that high intake of omega-3 PUFAs like EPA and DHA can increase brown and beige fat activity, increase expression of USP1 and other thermogenic genes, slightly increase energy expenditure and diet-induced thermogenesis. So in theory, more saturated fats in your adipose tissue plus more PUFA signaling could help your body produce heat more efficiently. In other words, a ketogenic or Arctic-style high-fat diet combined with gradual cold exposure might improve cold tolerance. But again, this is not solid proof that it makes you immune to the cold. For now, it's a hypothesis supported by indirect evidence. Now let me ask you something. Who usually follows a ketogenic or very low carb, high fat diet? Influencers, doctors, nutritionists, athletes, maybe even you. There's also a group of people who have been on something similar for thousands of years, long before the word ketogenic existed. Indigenous Arctic people, often known as Inuit or Eskimos. Many of them traditionally followed an Arctic marine diet, very high in fat and protein, and quite low in carbohydrates. Modern research suggests their traditional diet wasn't in deep ketosis all the time because of high protein and some carbs from glycogen in raw meat and berries, but metabolically still much closer to keto than a typical Western diet. The Inuit survive mainly on Arctic animals, especially seals and fish, and they eat almost every eatable part, raw or cooked. They also eat other Arctic animals. As we saw, Arctic animals have more unsaturated fats in their body fat. The Inuit eat the fat, absorb it, and store it with a similar fatty acid pattern. They get fat-soluble vitamins, A, D, E, K, from animal fats and organ meats, water-soluble vitamins and minerals from organs, berries, and other plants, vitamin C from raw or lightly cooked meat. Traditionally, they stayed active and relatively lean, especially the men, who are constantly moving and hunting. If I could prove that the Inuit have a much higher unsaturated to saturated ratio in their adipose tissue compared to other populations, this video would almost be done. I didn't find perfect data on that, but I did find some useful information. For example, there's a study, the Inuit diet, fatty acids, and antioxidants, their role in ischemic heart disease, and possible interactions with other dietary factors. This study shows that Inuit and other Arctic marine diet populations have high levels of long-chain and free PUFAs in blood or plasma or liver, thanks to marine animal consumption. It also states, high amounts of monounsaturated and omega-3 polyunsaturated fatty acids were found in adipose tissue. Even without detailed numbers, this is a strong hint supporting my theory that nutrition can influence cold resistance through fat composition and thermogenesis. Other research shows that the traditional Inuit diet often provides a very high percentage of calories from fat, especially from marine mammals and fatty fish, rich in MUFAs and long-chain omega-3 PUFAs, EPA, DHA, and relatively lower in omega-6 compared to Western diets. Over many years, their body fat becomes enriched in these more unsaturated fatty acids. This means their subcutaneous fat layer is not just thick, it's also more oily and less waxy, helping it stay softer and more functional at very low temperatures, and possibly making it a better insulator. Scientists have also measured basal metabolic rate, BMR, in indigenous circumpolar groups and found that their BMR is often higher than predicted for their body size. Men, about 7 to 90% higher, and women, about 3 to 17% higher. So their bodies burn more energy at rest, like a naturally revved up engine. More energy burned at rest equals more heat, which works together with fat insulation to keep them warm. When you pull data from indigenous groups in Alaska, Canada, and Siberia, men and women repeatedly show elevated BMR compared to standard prediction equations. This is interpreted as a metabolic adaptation to chronic cold. Interestingly, traditional Inuit don't necessarily have extremely high body fat. Many are fairly lean, especially active hunters, but because their subcutaneous fat is so rich in MUFAs and PUFAs, the quality of that fat might matter more than the quantity. More fluid, unsaturated fat stays softer at lower temperatures, wraps the body more evenly, helps trap a stable layer of warm air and reduce heat loss. So their unsaturated fat rich adipose tissue could give them insulation comparable to, or in some situations, better a normal person with almost double the body fat, but more saturated, harder fat. In other words, again, quality over quantity. Physiology studies of Arctic populations describe a mix of metabolic adaptations, higher BMR, and stronger non-shivering thermogenesis in brown fat and other tissues. Insulative adaptations, thicker subcutaneous fat, and stronger vasoconstriction in the skin to reduce heat loss. Combine that with a fat layer chemically tuned to be rich in unsaturated fats, and you get a better insulation plus better fuel for heat production in the cold. There are also classic cold room experiments comparing people from different ethnic backgrounds. In one famous study, nude African, Caucasian, and Eskimo men were put in a room at about 70 degrees Celsius. After about an hour, both the Caucasian and Eskimo subjects increased metabolic heat production much more than African subjects, who showed a smaller rise even after longer exposure. Reviews on cold adaptation also suggest that Arctic and temperate climate groups show stronger shivering and non-shimmering heat production and often have better cold-induced vasodilatation in fingers and toes. So the same chilly air temperature, an Inuit or other cold-adapted person usually ramps up heat production faster and keeps their extremities warmer than some from a tropical climate. Other genetic studies and another piece. Greenlandic Inuit carry special variants in genes that control how we process polyunsaturated fats, especially in the FADS gene cluster and other long-chain fatty acid metabolism genes. These variants likely result from natural selection from thousands of years of living in a cold climate on a high-fat, high omega-3 marine diet. They change how omega-3 and omega-6 fats are handled and built into membranes and adipose tissue. This makes it more plausible that their highly unsaturated body fat, their higher BMR, and these genetic tweaks all help their bodies act like efficient, fat-burning heaters with a flexible, insulating fat layer that still works in extreme cold. Put together, their traditional diet, higher resting metabolism, unsaturated fat-rich adipose tissue, and genetic adaptations all support the idea that what they eat and how their bodies process those fats help them live and function in the cold. If you've reached this part of the video, you've probably picked up the main idea. A higher intake of unsaturated fats results a higher ratio of unsaturated to saturated fats in body fat, resulting potentially better tolerance to cold and better function at lower temperatures. But I want to make something clear. Even if you somehow had extremely high levels of unsaturated fats in your body fat, imagine a crazy, hypothetical human with almost 100% unsaturated fat and 0% saturated fat. You could still freeze in very low, sub-zero temperatures. You'd still be at risk of hypothermia, frostbite, and death without proper clothing and protection. Fat composition can help you tolerate cold better, but it will never turn you into an invincible ice warrior. Realistically, these adaptations matter more in moderate cold, not in naked survival at minus 20 degrees Celsius. In theory, with more saturated fat and more active thermogenesis, you might find it easier to tolerate, for example, air temperatures below minus 15 degrees Celsius, water temperatures below 20 degrees Celsius, especially for short periods and with gradual adaptation. That could mean feeling more comfortable with cooler showers, slightly colder rooms, or using less heating for part of early winter without instantly shivering or suffering. But again, this is still speculative, and it absolutely does not mean you should recklessly expose yourself to cold or turn off your heating if it puts your health at risk. In reality, our bodies will never reach something like 100% EPA body fat. Human adipose tissue will always be a mix of saturated, monounsaturated, and polyunsaturated fats. As far as we know, no animal on Earth has perfectly 90 to 100% unsaturated fat in its adipose tissue either. So there are clear limits to what fat composition can do. Even if we are not like the Inuit, who have lived and evolved for thousands of years in cold climates, I'm still confident that a special diet like theirs, or an Arctic diet, could increase tolerance to cold to some extent. I don't have solid scientific proof yet, but there are interesting studies that fit with what I've told you. Inuit who eat a lot of seals and fatty fish have more MUFA and PUFA stored in their adipose tissue. Studies show that what you eat actually changes the fatty acids in your body fat. Many cold adapted animals increase unsaturated fats in their membranes to keep them fluid in low temperatures. Omega-3 fats, like EPA and DHA, can activate brown fat, increase UCP1, and boost heat production in animals. In humans, meals richer in unsaturated fats often produce more heat after eating than meals rich in saturated fats. I'll leave these studies and sources in the description if you want to dive deeper. So even if nobody has done the perfect human experiment yet, the pieces from anatomy, biochemistry, zoology, brown fat, nutrition, and anthropology all fit together in a way that makes this theory very interesting and biologically plausible. Maybe someone who sees this video will turn it into a proper experiment, or maybe one day I'll test the Arctic diet on myself, safely, and see how much it changes my own cold tolerance. If you, yes you, want to help test this theory in the future, you could try an Arctic style diet I'll be working on, and then tell me whether it improved your cold tolerance. And please, if you do this, don't just stop heating your house, be smart and safe. I'll never give up hope, and I'm hoping for the best. Alright, another video, another week of work. I hope you enjoyed this and learned something new from the information I presented. If you have video ideas, notice things I might have missed, or found mistakes, please let me know in the comments down below. Until next time, I'm wishing you a wonderful day or night. Stay healthy.